All right. When a substance undergoes a phase change, the temperature remains constant until the phase change is completed. Why is that? Because when a substance undergoes phase change, you now have enough energy to break, if we're heating, to break intermolecular forces, or if we're cooling, to create intermolecular forces. When a substance undergoes a phase change, all of the energy goes into intermolecular forces being made or created. Okay. For example, I usually like to start with heating. You know, there are possible um, there are five possible parts to a heating cooling curve. You do not always have to have all five. Okay, I'll explain that in a moment. But let's imagine that I take some water and I put it in the chest freezer in my basement. Okay. And my chest freezer in my basement is like negative 10 degrees Celsius, keep it kind of cold, right? Okay. So I've got solid ice. I'm going to make a graph of temperature and we're going to heat this thing up. Okay. I'm going to start here at negative 10 degrees Celsius. So I take this cup of rock solid ice, right? And maybe I planned ahead and I suspended a thermometer in there, right? How smart would that be? So I froze this thermometer in here, and right now that thermometer is reading negative 10 degrees Celsius. I'm going to take this cup of frozen water at negative 10 degrees Celsius. I'm going to take it out of the freezer. I'm going to put it on the table. Okay. And I'm going to say, well, what happens? What's going to happen? And a lot of times people say, well, it's going to start to melt. And the answer is actually not going to start to melt right away. Water melts and freezes at 0 degrees Celsius. I ain't at 0. I'm at negative 10. So the first thing, if you actually did this, you could do this at home. If you got, the freezer in your regular refrigerator is like negative 2. You do this if you got a thermometer. What's actually going to happen is if you watch this thermometer, before you see this thing start to melt, that thermometer is actually going to climb from negative 10 up to 0. So the first thing we actually have to do is we have to warm up to the freezing point. So this is going to warm up from negative 10 to 0 degrees Celsius. That's what I like to call the first potential part to a phase diagram. Okay, I call that the warming of the solid phase. You got to warm it up till it starts to melt. But then once that thermometer climbs from negative 10 to 0, then you're going to start to see some melting, right? And the amazing thing, which is absolutely amazing, is that, that thermometer, so you have liquid water here and the ice cube's going to shrink. That thermometer is not going to change again until the last speck of ice is gone. So if you had a stir bar in here and you had this stir in and this was, this thermometer would stay at 0 until the last speck of ice is gone. Because when a substance undergoes a phase change, the temperature plateaus. That's what I call part 2. Okay, the temperature plateaus during a phase change because when this warms up to 0 degrees Celsius at 1 atmosphere pressure, we have enough energy now to start breaking some hydrogen bonds, in case water, and all the energy goes into that. It doesn't go into making the temperature go up. It goes into breaking intermolecular forces. That's why we get a plateau. Now, once the last speck of ice melts, then you're going to see the thermometer start to climb again, and it would climb until we hit room temp, because this thing was just sitting on the table here, so it's going to climb up till his room temperature is about 20. But what if I take that now and I pour it in a pot, I put it on the stove, okay, and I turn the stove on. Well, now the temperature is going to continue to climb. And it's going to climb and climb and climb and climb and climb 30, 40, 70, 80, 90. It's going to climb and climb and climb and climb until the water starts to boil. So if I got this on the stove now, okay, it's going to climb until we hit 100 degrees Celsius. And then when the water starts to boil, that's when we're actively going from the liquid to gaseous phase. And you're going to get a plateau. Now, if you were doing this in your home, that is all the hotter you are ever going to be able to get that. Okay, you are not going to be able to get it above 100 degrees Celsius because it's plateaued. Okay, How would you get the water to be above 100 degrees Celsius? Well, this would not be safe. This would absolutely not be safe because of Gay-Lussac's law, which you learn in Chem 101. Okay, what you would have to do is you would have to put a lid on this and you'd have to seal it up. So you'd have to heat this as a closed system, which is dangerous because heating a closed system increases the pressure, Gay-Lussac's law, and it could explode. So please don't try this. Okay, all the other parts of this be totally safe to try at home, right? Where you heat the solid, melt the solid, heat the liquid, boil the liquid. But if you wanted to get to water, steam, okay, that is hotter than 100 degrees Celsius, what you would have to do is you'd have to put a lid on this, seal it up, and you would have to boil this water and turn it into steam and keep the steam in the container. And what I'm telling you is that that thermometer will stay at 100 degrees Celsius until the last drop of liquid water has vaporized. Once this is a container full of steam, then that temperature will start to skyrocket. And that's what I call the fifth potential part, which is heating the gas, right? So the maximum number of parts to a heating cooling curve that you can have is 5, right? You can have heating the solid, melting the solid, heating the liquid, boiling the liquid, heating the gas. That's the maximum. Now, you don't always have all the parts, right? What if I just take room temperature water and I heat it up to a boil? Well, that would just be part of 3, room temperature, heated up to boil. That would just be from here to here, right? I mean, that's all you would have. Like, it would just be 3 and 4, part of 3 and 4. You don't have the whole thing. So you don't always have all of the potential parts, but you can have up to 5 parts of the heating cooling curve. Now, what we're going to do is we're actually going to calculate the amount of energy needed to, heat ice cube at -10 up to steam at 135. Okay. How are we going to do that? Well, we have 2 different formulas, really. Okay. And it depends on whether or not we are on a slanted portion or if we are on a plateau. When you are on a slanted portion, which I am calling parts 1, 3, or 5, when you are warming the solid, warming the liquid, warming the gas, when you're on a slanted portion, because the temperature is changing, we can use that formula from Chem 101 that says the amount of heat needed is equal to the mass times the specific heat capacity times the change in temperature. A lot of times they call it Q equals MCAT. Q equals MCAT. There's no A. I never really got that, unless you think the delta sign looks like an A, which is stupid. But anyway, that would be Q equals MCAT. Great. Right? Heat equals mass times specific heat capacity times change in temp. That's the formula we need on the slanted portions. Now, the specific heat capacity is going to change. The solid form of a substance has a different specific heat capacity than the liquid form, which has a different specific heat capacity than the gaseous form. For example, for water, the liquid form of water has a huge specific heat capacity, 4.18, and then the solid and the gaseous forms have lower. This is 2 point something. I think that's 1 point something or maybe 2.0. So they're much lower. It's almost, depends on the substance. But for water, it's harder to heat the liquid than the solid. And usually the easiest thing to heat for a substance is the gas phase. I'm sure there's an exception out there, but usually that's the case. When you are on a plateau, well, you have to use a totally different formula. Let me explain why. Okay, this formula ain't gonna work. When you're on a plateau, the temp's not changing. So my change in temp would be 0, which would make this whole thing 0. And what that would imply is that to boil a whole pot of water, once you heat it up to boiling, it just instantaneously vaporizes, takes no energy. Of course not. It takes a heck of a lot of energy. Once I heat a pot of water up to a boil, I got to keep it on there for a while if I want to turn it all into steam, right? It takes an immense amount of energy to make that happen. But we can't use the same formula. When we are on a plateau, which I am calling parts 2 or 4, we'd have a different formula. The amount of heat when you're on a plateau is equal to the amount of substance, that's moles, folks, times some constant, enthalpy of something. Now, the constant, when you're going from solid to liquid, that constant is called the enthalpy of fusion. And the constant when you're going from a liquid to a gas, that constant is called the enthalpy of vaporization. So enthalpy of fusion, enthalpy of vaporization. So these problems can get a little complex, right? Okay, if I've got all 5 parts to my heating cooling curve, then I got some work to do, man. That would be 3 Q equals MCAT problems and 2 Q equals N times delta H, either fusion or vaporization, depending on what I'm doing. So there's really 5 problems. It can be up to 5 problems in one. Let's take a look at one of these. Here we go. Is everything I just talked about. I don't want all that. There we go. All right, folks. I'm going to say this now, and I'll still get 3 emails, and that's okay. Here are, like, there's a homework problem where you're going to have to do a heating cooling curve. Here are the constants. So on this slide right here, okay? Don't worry about it. You can still email me, and I'll still be polite when I email you back and say, hey, it's on that slide. Remember that slide I was telling you about? It's this one right here. Or when in doubt, you could Google. It's amazing, right? Hey, Google, what's the specific heat capacity of steam? Oh, there it is. Great. That'd be a slightly different number, right? Than 2.0. Maybe they give you 1.95. I don't care. Whatever. It's fine. Anyway, when in doubt, Google it. But for this one, go back to the slide. I want to do this problem. Okay? So we have a whole bunch of constants at the top. I want to know how much heat energy in kilojoules would I have to put in to take an 80-gram block of ice out of my chest freezer at -10 and turn it into steam at 135. Maybe, I don't know why you would ever do this, but maybe I'm taking that 80-gram block of ice out of my chest freezer and I'm putting it in a oh my God, I'm going to put it in a pressure cooker, right? That's how a pressure cooker works, by the way. Pressure cooker, because it's a closed system, heats that water up well above 100 degrees Celsius. That's how you can cook like a whole like shank of beef in 2 hours or something, right? Okay, because the water's hotter than 100. If you boil water, the hottest it's ever going to get is 100, right? But if we have it in a closed system, it can get hotter than 100. It's pretty awesome. Anyway, the first thing you want to do when you get one of these problems is to draw an accurate heating cooling curve and to label all the parts on the y-axis, which is temperature. So that's the first thing we're going to do. If you give me a second, this one's going to be one with all 5 parts, right? So if you can do this one, you can do any of them. So here's where my heating cooling curve is going to go. And we are starting with ice at -10 degrees. Excuse me, -10 degrees Celsius. So we got to draw and we got to get up to steam at 135. Oh boy. Well, what's going to happen? Well, the first thing, we got to heat the solid up to 0. See how I labeled 0? And then we got to melt it. And then we got to heat it up until it boils, which is 100. Then we got to boil it all in a closed system like a pressure cooker. And then we got to heat it up to 135. Then I like to label the parts. So heating the solid, melting the solid, heating the liquid, boiling the liquid, heating the gas. Now, we need to do the math. When you're on a slanted portion, it's Q equals MCAT. When you're on a plateau, it's Q equals N times delta H fusion and delta H vaporization. Okay, so here we go. Let's do number 1. This is going to be a Q equals MCATer. We said that the mass of the piece of ice, I'll pop the problem back. I can pop the problem back up there right now. The mass of our block of ice is 80 grams. So we got an 80.0 gram block of ice. And we are in the solid phase to start. So we need the specific heat capacity of ice, 2.092. So 2.092, 2.092. And specific heat capacity has complex units. This is a complex thing, which are joules per gram times degrees C. And now I need the change in temp. Well, the change in temp, if I'm going from -10 to 0, that's a 10-degree temp change. sig figs, give me 2 or 3, whatever. We're really going to worry about it at the end. So if you pop this in there, for step 1, we got, grams cancel out, degrees Celsius cancel out. We're left with joules. So 80 times 2.092 times 10, that's 1,670 joules. That would be the amount of energy needed just to warm that ice up to start to melt, just to start to melt. And now step 2. Step 2 is our melting portion of this. And when we're on a plateau, we're going to use Q equals N times delta H fusion. Now, delta H fusion, that's going to be on the slide. But before we get there, we need the moles. Now, if you take physics, they will use mass here, and then they have converted these constants into kilojoules per gram. And I just don't. Technically, it's amounts, it's moles. But the physicists don't like moles very much. They're scared of them. Okay, really, but anyway, we need to get moles. How do we get moles? That's molar mass, man. 80, I'll do it over here. 80.0 grams of water. That's 18.02 grams in a mole. So 80 divided by 18.02, that's 4.44 moles. So my N is 4.44 moles. And now we need to grab that change in enthalpy of fusion off of that slide. And the change in enthalpy of fusion, 6.008 kilojoules. Be careful, that's going to matter in a moment, per mole. So that's 6.008 kilojoules per mole. Moles cancels out. We'll be left with an answer in kilojoules. And I'm going to do 3 sig figs, 26.7 kilojoules. So what did we just do? We did part 1. We did part 2. Here's what I want you to do. I'm going to pop that slide back up there in a second so you can have the specific heat capacities and the delta H of vaporization for step 4. I want you to calculate the amount of heat needed to heat that water up from liquid water at 0. Because right here is all solid. This is ice at 0. This is a mixture. And right here, this is all liquid water at 0. So we've turned it all into liquid water. I want you to tell me how much energy is needed to take that up to liquid water at 100. Then I want you to tell me how much energy is needed to turn all that liquid water into steam. And then I want you to tell me how much energy it is to heat that steam up from 100 to 135. So I'm going to pop the constant up here. I'm going to give you like 2-3 minutes. And I want you to try your best to get the answer for portion 3, portion 4, and portion 5. Give it a shot. Right. Cool. Here's what you should have, folks. We did 1 and 2 together. The amount of energy needed to warm the solid, 1,670 joules. The amount of energy needed to melt the ice, 26.7 kilojoules. The amount of energy needed to warm that liquid, 33,500 joules. The amount of energy needed to boil all that liquid, a whopping 181 kilojoules. And the amount of energy needed to warm the gas, 5,150 joules. This problem wants to know the total amount of heat. And to get the total amount of heat, we got to add these together. Now, the problem is this, okay? When you are using Q equals MCAT, so steps 1, 3, and 5, when you're doing Q equals MCAT, your answers are in joules. But when you're on a plateau, 2 and 4, your answers are in kilojoules, okay? So the problem is we actually need to change these into kilojoules before we can add all 5 steps together. And then what's going to happen is then we're going to have to worry about addition, subtraction, sig fig rules. And really, the 181 kilojoules is stuck at the ones place. Our answer is going to be stuck at the ones place anyway. Moral of the story, listen, that's a lot of sig figage, right? You got sig figage at each step. You got sig figage overall. When I grade a problem like this on the test, I'm not going to grade this particular problem for sig figs, right? Because it's way too many steps, right? Do your best, right? But this particular problem, not going to nail you on the sig figs, okay?
All right, appreciate it.
Yeah, awesome question. Okay, so here's the problem. before we get the total amount of heat, we got to be in the same unit. So we got joules, kilojoules, joules, kilojoules, joules. If you look at the original problem, it wants the amount of heat in kilojoules. So we need to convert those slanted portions, the slope portions, into kilojoules. How do we do that? Divide by 1,000. Now, if you want to write it out, there's 1,000 joules in a kilojoule. That's totally cool. Or, if this is, if you can move the, whatever, right? So that's 33.5 kilojoules, and that's 5.15 kilojoules. Now, here's what I was saying to Loudon, okay? Now we got to add them up. And when you add them up, addition, subtraction, sig fig rules is all about place value. I'm going to stop at the ones place because this portion right here, got me 181, and that's just the ones place. So I'm gonna stop at the ones place. If you went to the 10th place or 100, it's fine. I won't take all points. So anyway, we got to add these all up. Here we go. 1.67 plus 26.7 plus 33.5 plus 181 plus 5.15, and we're going to get 248 kilojoules. So now ladies and gentlemen, if you take a 80-gram block of ice out of a chest freezer at -10 and you put it in a pressure cooker and heat it up to 135, that's going to take 248 kilojoules of energy. Yeah. Here's an interesting fact for you, okay? If I took 80 grams of steam from 135, do this in purple. If I took 80 grams of steam at 135 and I cooled it down to a block of ice at -10, so if I went in the opposite direction, but I did the same thing, then instead of releasing 248 kilojoules, or I'm sorry, instead of requiring 248 kilojoules of energy, it would now release 248 kilojoules of energy. So oftentimes for me, when I do these problems, it's easier for me to imagine that I'm heating the substance. So if the problem was really how much energy is released when 80 grams of steam at 135 is cooled to a block of ice at -10, I usually just pretend I'm going the other way. Block of ice at -10 to 135, and then I just say, well, it'd be the same amount of energy. Law of conservation of energy, right? So if it takes 248 kilojoules to go this way, then it would release 248 kilojoules if I was cooling. The heating and cooling curves are just opposites of one another, right? So if I was cooling steam from 135 to -10, I'd just make that a -248, and the negative sign just means releasing energy in the end. So sometimes you get a cooling problem, and if you want to draw a cooling curve like the one I just did here in purple, totally cool. If you don't, you can draw a heating curve and then just either say released at the end or make the answer negative.